So welcome again, and I hope you are ready to continue to the second distributed MPC, and it is about non-cooperative DMPC. Let us forget about the cooperation. Why cooperate? It's costly. It doesn't guarantee finding a solution. And yeah, you could ask why we don't use the optimized results of our neighbors. I can say, okay, let me just optimize for myself what my neighbors tell me about their results, about the results of their optimization problems. I put in my optimization problem, consider them this way, and it should be fine. So this is the same graph as in cooperative DMPC. And here it is similar. Each agent sends the states, references, parameters to its controller. It considers also passive agents, and it receives the optimized inputs, the current measured states, and the parameters of the neighbors, and consider them in the optimization problem, compute optimal inputs for the own agent, apply these, and it's fine. Why we don't do this? So as you noticed, this is greedy, consideration only of the own objective function, own constraints, and the coupling objectives and constraints with neighbors is greedy, because we look just at our goals, at our optimization problems, and just consider what we know about the neighbors, their optimization results. And what we have here also is that we use the communicated optimized predictions of neighbors, and communications always include time delays. So there is no zero costly communication. It takes always time. So do you see a problem in this formulation here?
Here it's like if it is sequentially. Here we have an order in how to say it, in solving the optimizations. Is each time for agent 2 I have to wait till I get the optimization and all the informations of the solution of the optimization of agent 1, then I could start optimizing for agent 2, and this may create big delay and maybe faulty solutions that may lead to collision in reality.
Yeah, Manan, you are speaking about the solution. We will get to it, but the problem is actually the time delay. What we saw in the pedestrians example, we optimize at the same time, exchange the plans, and take the old plans, use them in our optimization problems, and solve the optimization problem again, and this leads to conflicts. This is actually the problem in the pedestrian example, that we optimize, communicate, optimize, communicate, and we have always at least one time step old plan. So when I say plan, I mean the optimized predictions, right? So the plan in agent 1 in this example here is one time step after 2 has solved its optimization problem. Right? If we would compute here in parallel. Well, this doesn't satisfy the prediction consistency property due to the time delay of communication. So we have an outdated plan of our neighbors. So for the computation time, it is totally fine. We take just computed plans from our neighbors and use them in our optimization problems. So it is easy to consider them in the optimization problem. The optimization problem stays small, but prediction consistency isn't guaranteed. So we look at the example of pedestrians, but this time with vehicles. Vehicles move with the same velocity. Here the red vehicle 1 moves from west to east, 2 from east to west with the same velocity, and the vehicles are located symmetrically with respect to the vertical axis. So you see here. And we assume a time delay of 1 time step. Well, remember the pedestrian example. 1 computes a plan, doesn't see any or let's say actually if we consider also the geometry of the vehicles, and here actually there is a collision because the points, the centers are near to each other, and each of the vehicles knows the plan of the other vehicle from step 1. That means vehicle 1 takes this plan of 2, put it in its optimization problem, and compute this trajectory to avoid 2. And 2 does the same, right? And this leads to the collision here. Because the algorithm is greedy, vehicle 1 and 2 think at the same time, okay, the other vehicle is going to avoid the collision. Why I should do it? I can go back to the reference trajectory. By the way, the reference trajectory is just here, the straight line on the x-axis. Right, both think, okay, let me go back to the reference trajectory, and again, there is a collision. Both think, okay, I have to do something to avoid the collision, and again, no solution, and at some step, we cannot avoid the collision anymore. Right here, just a reminder of the pedestrians walking. If you want to repeat the example now with the knowledge of DMPC. And if we look at the coupling graph of non-cooperative DMPC, the problem is that agents consider each other at the same time. So we have a consideration of exactly the same coupling in each of the coupled agents, right? And if you look deeply into the coupling graph, actually it was undirected. And undirected means it's directed in both directions. Well, so cycles in the coupling graph contains cycles between the agents, And cyclings in coupling graph lead to loss of the prediction consistency property, as you now see. So agents consider each other at the same time, and this leads to the conflict, right? There is also another term for prediction consistency you may find in literature. People speak also about conflict resolution. So I'm speaking here about prediction consistency, about the what I want to reach, and some people speak about a conflict, and we want to avoid the conflict. It is at the end of the day the same. So I think the prediction consistency property is also well defined and is both are fine. So what can we do? A solution is solve in sequence, what Manuel suggested, and iterate. We can not just solve in sequence, and also we can iterate to get to a better solution. Of course, we have to have a strategy there, not just iterate over all agents. You should know what you're doing, but this leads to high computation time, right? So we actually switched to non-cooperative to reduce the computation time. And now the solution is solve in sequence. And again, we have the high computation time. And if we iterate, then we can forget about real-time application, right? And yeah, at this point, the work of my group comes. We propose the priority-based non-cooperative distributed MPC. So a lot of words here in the name of the method, but actually it is simple to understand. So here where you can find details on the model or on the method. So yeah, in these pages. Yeah, and the solution we suggest is distribute priority in the network, and the priorities, of course, should be distinct. So they so a priority per agent, and lower priority values correspond to higher priority. So it is just a definition here. This is the priority of agent 1. It is 1, just in this example. Of 2 is 2, of 3 is 3, and of 4 is 4. Of course, you can have different priorities, but in this example, I choose them the same as the vertex name, right? So we have here priorities. So the priority of 2 could be also 1. Yeah, depends on many things. Maybe we are going to discuss here. Nice. Again, what we do here with passive agents, because we are going to introduce a structure in our network, and we have also to consider the passive agents. They have the highest priority in our network. And here we consider the own objective function, on constraints, and only the coupling objectives and constraints with higher priority agents. So in non-cooperative, we consider the coupling with neighbors, but here we limit this to the higher priority neighbors, which means here 2 considers 1. 1 doesn't consider anybody. 3 considers 2, and 4 considers 1, 2, and 3. Else it is here the same as in the last slide or some slides before when I introduced non-cooperative DMPC. So do you have questions about the concept?
I have only one comment about the priorities, how they are assigned. I mean, is it based on the information that that agent may provide to the actual agent? Or, for example, if we want to avoid obstacles, maybe we can set priorities based on the relative distances,
Yeah.
or speed, or how?
Yeah, you asked the question and gave an answer, and I'm going to speak about the answer in more detail. So it depends on two things mainly, on computation and communication, and on the application. So as always, reduce computation and communication, and reduce computation and communication is one thing I'm going to present, how to reduce these, how to distribute the priorities to reduce the computation time and communication, and it depends on the application, and I'm going to show you examples for applications where this method is good, where this method is also not very good, and where the priorities decide on things like feasibility. So I think we continue again the same example of non-cooperative DMPC, but this time against priority based, and as you would assume, there is a solution, right? V1 assigned here the higher priority, so it doesn't consider V2, and V2 is assigned the lower priority 2, and it considers 1. So 1 just continues in all steps on its reference trajectory, and 2 takes the effort of avoiding the collision. So we see here that it works, and if we look at the coupling graph, we need to have an acycling, because we said cycles are problem or cause problems. So we need to have directed acyclic coupling graph, and using the method I presented, assigning priorities to vertices and connecting the vertices depending on the priorities leads to a directed acyclic coupling graph. There is also an abbreviation for this, is DEJ, and yeah, the proof of this, that we always get an acyclic coupling graph, can be done using the adjacency matrix, but I'm not going to go through that proof here. So just that you know that there is a proof.
Okay, can you hear me? Oh, yes. So just one question on the last slide for vehicle 2. The computational effort is now equal to the cooperative DMPC, right? So just for vehicle 2, because it has to solve the optimization problem for vehicle 1 and 2.
No, not exactly, because 2 gets the optimized solution, the plan from one. It doesn't solve the optimization problem of one. It uses the result of the optimization problem of one.
Okay, thank you. Yeah.
But the optimization solution from one outdated by some time step, or?
Yes, we are going to speak about this problem in a minute. So we assigned priorities to avoid sequential computations, right? And yeah, I speak about it in a minute. So time delay of predictions of higher priority neighbors, what you said now, Chao, they are outdated, right? So we are done in case of time invariant coupling topologies. So I introduced this term to you yesterday. And if we assume bounded disturbances in higher priority neighbors. Yeah, at the same time, if we assume bounded disturbances, we assume also good controllers. So controllers who could get rid of the disturbances. So this means here, if vehicle 2 can rely on the prediction of 1, then we can compute in parallel, right? This is this point. So if the controller in 1 is good, and it tells us outdated plan, but we know that its controller is good and it can count for disturbances, or that disturbances are bounded, then we can rely on its prediction, and we can use, in this case, an outdated prediction. And if if the network is time invariant, if the network doesn't change with time. So you can imagine we use outdated plans, and a condition for this is that the network doesn't change in time, because if it changes in time, then we cannot use outdated plans. So this is just a condition for using outdated plans.
Sorry, maybe this is some like detailed formulation. So like the outdated prediction that we use, I mean, do we just use that part, or like do we like somehow do a few step of predictions so we get like the value for the neighbor for the whole prediction horizon of my own agent, if you understand what I mean?
Yes, you're right. In my work or in my group, we continue the prediction with delta U equals 0. That means we hold the value of the control input to predict the missing steps. So the question of Chao is actually a good question. Maybe I can draw it here. HP, this is T, and the plan we get into about 1 is, let's say, let's assume just one time step of delay. We get some plan like this, and actually, no, I should write here HP minus 1. actually T plus to be more precise. Yeah, the plan we get from one is outdated, and it looks like maybe this, right? And actually at the current time step, we are in at time step 1 or at time step T. So we should delay this part and add something here, right? This is your question, Sharon.
Yes, exactly.
Yes, and what we suggest here is just to keep delta U 0, as it is common in MPC.
Okay, I see.
Yeah.
Thanks.
Welcome. But this is also a detailed point where you also can put some effort to get something better. Well, here we have the point loss of prediction consistency property in case of time variant coupling topologies. And that means this approach of priorities and parallel computation we cannot use in a time variant coupling topology. So if the network is time variant, I firstly want to demonstrate this using this example. So we have here 3 vehicles moving with the same velocity, V1, V2, and V3. So V1 is moving from north to south, V2 and V3 are moving from west to east, right? These are the moving directions. And they have to follow the straight lines. So V1 and V2 would collide in the origin if they would continue moving, right? And we assign the priorities. V1 gets the first priority, V2 the second, and V3 the third, which means V1 doesn't consider 2 and 3, 2 considers 3, no, 2 considers 1, and 3 considers 2 and 1. Maybe I can draw it. V1, V2, V3. So V here stands for the vertex in the graph, but at the same time, you can think of it as the abbreviation of vehicle, right? It is the same. But we speak in general about agents. So V1 is considered in 2 and 3, and 2 is considered in 3. So in this scheme, you could, or you may think, okay, they could also compute in parallel, but no, because the network is time variant. And the time variance here is that the vehicles were, or the predictions of the vehicles, so the prediction of vehicle 2, okay, maybe I'll say it again. So the prediction of vehicle 1 was not in the prediction of vehicle 2. So the set of the prediction of vehicle 1 was not inside the prediction of vehicle 2, and the prediction of vehicle 2 and vehicle 3 are parallel, which means that there is a coupling between 2 and 3, of course, here, but the coupling is inactive, we see, right? And at this point, so at one time step, V1 doesn't consider anybody, vehicle 2 considers vehicle 1, and vehicle 3 considers 1 and 2. 3 doesn't see 1 in the prediction, right? Time variant, it changes with time. And 2 sees 1 and reacts to it. And here you see in the prediction of 2, it starts avoiding 1, but 3, they didn't know about 1, and there is a conflict between 2 and 3 in the prediction here, right? If you would simulate this example, you will not see any collisions between the vehicles, but in the predictions. And we want to have consistent predictions, right? Maybe we can construct an example where we have collisions.
Can I ask something?
Yeah, please.
So in this example, obviously someone had to give priorities, and if you were to implement this on multiple vehicles, who sets the priorities when they encounter each other at an intersection?
I'm going to speak about this point in
okay.
In a minute. Okay. So, well, I want you now to understand this example and to understand that the prediction consistency property is lost in this example. Is it clear to everybody?
For me, it's not clear for V3 why you said that V3 doesn't see V1, even if there is a coupling between them. Or maybe I catch it wrong, I don't know.
Yeah, maybe I didn't explain it in detail. Maybe I'll take here an example of 2 vehicles. So assume the prediction horizon of this is 1, this is 2, and this is the prediction horizon of 1, and this is the prediction horizon of 2. In the graph, they are coupled, but the coupling is inactive because the prediction horizons do not collide. So the vehicles do not collide actually in the prediction horizon. So if now they continue to the next step, so we should add here also 1 step in the prediction. The constraint is still inactive, which means also that the coupling is inactive. The coupling is there but inactive, and they continue moving till the coupling gets active. Right, that is what I mean with active and inactive couplings. And I defined that if I have inactive couplings which can become active in a network, then the network is time variant. Because you can consider inactive couplings as there is no coupling at a time step t, and it appears at a time step t plus 1 or plus k in general. And that's why such a network is time variant. So we don't have just to consider the static coupling that we say, okay, at some point in time, there is a coupling between 1 and 2, but we have also to consider the time when there is a coupling and when is this coupling active or inactive. So guys, you have good questions. Just if you have question in mind, just turn on your microphone and ask. So I'm happy about your questions. I mean, it is new to you, this network thinking, and for me, it is clear, and I try to transfer it to you. Maybe I think, okay, something is trivial, but maybe it is not. Actually, this problem of the prediction horizon, that the prediction horizon of MPC is limited, is naturally a problem of MPC, not of networked MPC. But yeah, the problem is transferred from MPC to Net-MPC. But you find the same problem also in MPC. The natural of MPC is to have a limited horizon, and MPC just sees or sense inside the horizon, and outside the horizon, the MPC doesn't know anything about things about outside the horizon. And that is a general theoretical solution to this, also in MPC, to have an infinite prediction horizon, and it is not implementable in real time, of course. So we can here extend the horizon, that the constraints are always active, right? When they should be active, right? So here, maybe an explanation to this. Assume that we go to the time, okay, we assume we are here at time step t, okay, it is 1. Assume we go to the last time step to 0, and we extend our prediction horizon of 1. Then we get the same problem again, right? Got it? So extending the prediction horizon leads to earlier consideration of conflicts, right? And if we have an infinite prediction horizon, then we consider all possible conflicts in the future, and the conflict is solved, but this is not realistic, right? And the solution here is incorporating a sequential algorithm into the priority-based non-cooperative DMPC, and this is what we are going to do here. So sequential algorithm is based on the coupling graph. So priorities mathematically generate a partial order, and in general, you can check this also in math or computer science textbooks, or maybe you go just to the internet. We can convert every partial order to a topological order. And how we do it, we renumber the vertices of the coupling graph with their corresponding priorities. So now the name of each vertex is its priority. And this priority is a valid consequence of solving the optimization problems, which means now that we solve the optimization problem of the highest priority agent first, then of the second, of the third, and so on. Right? Now we have a sequence in computations, and this is just possible if the graph is directed acyclic graph. So we can convert a partial order to a topological order if the graph is directed and acyclic. Okay, the good news here is that our topological order isn't unique. And this allows us to parallelize subsets of the optimization problems of the agents. And how we do it? So here is the algorithm to determine parallelizable vertices. The input is the adjacency matrix of the directed acyclic graph. And the output are the parallelizable vertices saved in a matrix L, just like level. And let me explain you the algorithm using this example. Or first, in general, the algorithm works like this. In a directed acyclic graph, always we have at least one vertex without incoming edges. This is a property in directed acyclic graphs, right? You can assume, or you can imagine maybe, if we have a graph without cycles, we should start at some point, right? And there is no incoming edge at this or at these vertices. So we take these vertices without incoming edges and put them in the first level. So these, maybe I said edges, I mean vertices, right? So we delete the edges of, or these vertices have outgoing edges. We delete these edges and look again in the graph for vertices without incoming edges and put them in the second level. And now again, we delete the outgoing edges from these vertices. Look again in the graph for vertices without incoming edges and put them in the next level, and so on until we don't have edges in our graph. So to apply this algorithm here in this example, so here we have agent 1 with priority 1, 2 with priority 2, 3 with priority 3, 4 with priority 4. 1 is connected to 2, so 2 considers 1. 3 is connected to 1, and 2 and 3 are connected to 4. How can we find parallelizable vertices in this graph? We look for the vertices without incoming edges. And in a directed acyclic graph, at least one exists. And this is, so I'll take another color. This is V1. We take V1 and put it in the first level. Now we delete the outgoing edges of V1, right? So it doesn't have incoming edges, but outgoing edges. So we delete them and look in the graph for edges without incoming, again, for vertices without incoming edges. And these are 2 and 3 now, right? If we delete E12 and E13, then we have 2 and 3 without incoming edges. We take them and put them in the second level. And we delete the outgoing edges from them. So we delete E34 and E24. And the remaining vertex is V4. We put it in the next level. So as you see here in the resulting coupling graph, here, you see that V2 and V3 depend on 1, and V4 depends on 2 and 3, but not on 1, and 1 doesn't depend on any agent. And these can be used as levels of computations, which means here V1 should compute first. V2 and 3 can compute in parallel. So this is about determining parallelizable vertices, because 2 and 3 don't depend on each other. They can compute here in parallel, and V4 can compute after V2 and V3, and we have 3 levels of computations. Without this algorithm, we had 4 levels of computations. Of course, this is a simple example. In more complicated examples, we could find, it depends on, of course, on the coupling between agents and on the density of the graph, if we find more or less parallelizable vertices. So the rules for parallel and sequential computations are as follows. Agents on the same level solve in parallel. This means 1, 2, and 3, then 4. If disturbances of agents on the first level are negligible, agents on the first and second level solve in parallel. This is what we saw in the example of the 2 vehicles driving towards each other. If we can assume here that the agent number 1 has the limited disturbances, or let's say bounded disturbances, or we can assume that its controller is good enough, then we can use outdated plans of 1 in 2 and 3, because we can rely on it, that it will not change a lot, right? And of course, it depends on the bound, how 1 changes its plan. To some extent, we can accept changes. To some extent, we have then to use maybe robust methods to count for uncertainties. And maybe the simple solution could be just compute 1 first, then 2 and 3, then 4. So agents on level 3 to NL. NL is just the number of rows here. So NL is here 3. Solve sequentially after agents on level I minus 1, which means here that level 3 computes, then level 4, then level 5, and so on till NL. The algorithm is executed repeatedly in case of change of the coupling graph. As you would, this is natural. If the coupling graph changes, we have to compute the parallelizable vertices again.
I think that the algorithm used to parallelize the vertices is an algorithm that is used in management in CPM networks. It's here we have to kill all the time the predecessors. I mean, what precedes the vertex, and we take into account the successors.
I don't know the algorithm you are mentioning, but it sounds logical. Could you say it again?
I mean, this algorithm.
It's similar
to the algorithm used in management. If we have a project and we have multiple tasks, we how to say it? We present the task like vertices, and we have the costs
Yeah.
to make that tasks. And if we want to calculate the minimum time to realize the project, we use this algorithm. Each time we take into account, it's like that we how to say it, we convert the network to like this one, a parallelizable network.
Yeah.
And we calculate and we sum the costs assigned to each edge. When I saw this, it reminds me to that
Okay.
it is in CPM theory in management.
Okay.
So I
yeah.
see that those theory are used even here in MPC, so it's good.
Yeah, good for you that you know it. So it is, yeah, actually topological orders are common concepts in computer science. So always if you have tasks and you can parallelize something and you can represent the task as graph, you can use topological order, right?
Yeah.
So the link between computer science and networked MPC is here, let's say, the special thing. Yeah. The combination of methods to say, okay, we have to compute here in sequence. Why always in sequence? I can convert the graph to a topological order, and I can look for parallelizable things. And this is also a good research question, how to distribute priorities to get an optimal computation time.
Mm-hmm.
So if you are free in choosing the priorities, you could also ask the question, how can I distribute the priorities such that the number of levels is minimized? So, and the rules for distributing priorities is, this is one, how to distribute priorities to minimize or to save computation time. Yeah, at the same time, save communications. So means to have less links in the graph. Links means here edges. And on the other hand, it depends on the application. If the application allows or doesn't allow, you can also generalize some aspects of the application. For example, energy consumption. For example, in a crossing, in a road intersection, if we want to apply this and assign priorities to the vehicles, we can, if we want to consider energy consumption, we can say, okay, stopping a truck is more costly than stopping a personal car. So I would assign a higher priority to the truck if I want to save energy. This is a possibility. Other possibilities are to think about efficiency, how to distribute priorities, for example, in an intersection that the vehicles cross the intersection with optimal time. That means that we minimize the traveling time of the vehicles crossing the intersection. And I'll show you during this lecture also other examples where the distribution of the priorities also can lead to infeasible solutions. So here we see this example again, where we had loss of prediction consistency property, and using the concept of parallel and sequential computation, we can compute the optimization problems of 1 and 2 in parallel, V3 after 1 and 2. And yeah, as you can see, the prediction consistency property is satisfied.
Sorry, I don't really get why V1 and V2 are solved in parallel, according to the graph we had earlier.
Okay, why we can parallelize 1 and 2? This is your question?
Yes.
Yes. So one has the highest priority in the network, and it just follows its reference trajectory. It doesn't count for any other agent in the network. And if we assume that the controller of V1 is good enough and or the disturbances are bounded, then we can assume that V1 doesn't change its mind at every sample time. That means if we can rely on the predictions of 1. And in this example, or in this application, it is the case, because V1 is going just to drive from north to south, to the south, and it is not going to change its predictions from time step to time step. So we know in the second time step, I can delete the first prediction and add 1 to it, and the prediction consistency property will be maintained.
No, I mean, in the previous slide, you talk about this, like getting this topological order from the graph.
Yeah.
And then, so in this case, how does it end up with like V1 and V2 gets on the same level? That's my question.
Okay, V1 and V2 are not on the same level. So V1 is on level 1. V2 and 3 are on level 2. And V4 is on level 3, right? But if we could assume that the controller of V1 is good enough to follow the reference trajectory, or we can assume, maybe that the disturbances are bounded, that we can rely on the predictions of 1, that the outdated predictions of 1 will not change in the next step, we can use them in V2 and V3, and we can compute levels 1 and 2 in parallel, just if this assumption is feasible.
Okay.
Okay. Let us move on to a stability and feasibility discussion.
Can I ask something?
Of course.
In the previous slide, you said that V1 and V2 can solve in parallel, but from your explanation, can V1, V2, and V3 solve in parallel? So these three agents, so the level 1 and level 2.
Maybe I draw the graph. I didn't get your point. So this is the coupling graph of this example.
Okay. That's a different example. Okay, sorry.
Okay. Okay, maybe you were confused.
Yes.
This is not the coupling graph of this.
Okay, sorry.
Okay, let's move on to the stability and feasibility discussion. Our main assumptions were that the centralized MPC would generate a solution in each time step or in each sample time that is NCS stable, feasible, and optimal. We discussed this today. Considering each agent as isolated from NCS. So if we consider in our examples, each agent means each vehicle isn't in the network. So we break the links between the agents. Then the solutions of BB means priority-based, non-cooperative DMPC are agent feasible, stable, feasible, and optimal. Right? This means if we isolate the agents from the network, we break the couplings. Is the solution of our MPC stable, feasible, and optimal? Yes, we assume this. Right? It is just, I think, acceptable assumption, because here we assume that the MPC, not the coupled, the MPC, the normal MPC of each agent is good, is good modeled, and is and that we considered stability, feasibility, and optimality there. Okay. The satisfaction of the prediction consistency property in any NCS, even with time delays and time variant coupling topologies, is guaranteed using priority-based non-cooperative DMPC. Now, of course, it depends on also on the distribution of the priorities and on the application. This is a different thing, but I'm here speaking about the structure of the problem. And we can prove this using mathematical induction. So with other words, simply speaking, I have a network and I have a center. The center generates stable, feasible, and optimal solutions. And I have agents in my network, and I break the network. There is no network there. And each agent would generate a stable, feasible, and optimal solution. And now we put all agents in the network and run a priority-based non-cooperative DMPC, and using the priority-based non-cooperative DMPC satisfy the prediction consistency property in the network, which means that we get NCS feasible and stable solutions. Of course, if they exist, this is always an assumption according to solutions, if they exist. So the algorithm converges after only one iteration of sequence. Here we see a comparison of the optimization times of NCS in different Net-MPC strategies, because the communication effort is different and depends on, for example, the directions, and if it is directed or undirected, or if it depends on on the number of couplings and so on. We separate the considerations of optimization time and communication time that we look here. When we consider the computation time, we look at both optimization time and communication effort or time. And if we look at the optimization time, if we say from the DMPC, it is T optimization time. From the cooperative DMPC is the it is the maximum optimization time of all agents in the network. In our priority-based non-cooperative DMPC, we look at the maximum computation time of level 1 and 2. And we sum the computation times of the remaining levels. Right? This just says I have level 1, level 2, level 3, and I look at the I said OT. Let's say optimization time of level 1, optimization time of level 2, optimization time of level 3, LN, optimization time of level N, and the computation time of our network is the summation of these. But for 1 and 2, I can look for the maximum of both because they can compute in parallel. So if I would have a sequential iterative DMPC, then I have to count for the number of iterations and the sequence here. So obviously this is higher than this, right? Yeah, and here we look at a testing scenario of vehicles driving towards a center of a circle. In a minute, I'll show you the simulation of this example and also experimental results. But maybe I'll explain this example. So here we have vehicles distributed on a circle. They drive towards the center of the circle, and if the number of vehicles here is even, then they switch positions, right? This is the position, so they just switch their positions here. And in this example, you see here the different computation times. So here we see the medians and maximum values of CMPC, the priority-based non-cooperative DMPC, and a sequential computation. So the maximum of CMPC grows exponentially. Please consider that we have here logarithmic scale, right? And that of the priority or sequential are here, and of the sequential or of the priority based is always below of the sequential. In worst case, it is equal to the sequential one. And here we see the different objective values normalized to the objective value of CMPC, right? So in best case, we get the value of CMPC, and then we have a value of 1. That means here, this is the lower bound of our objective values of the network of the priority-based non-cooperative DMPC. So we compare them to CMPC. So just divide them by the optimal value of CMPC, and this is always greater or equal to 1, right? Yeah, and here we see it depends on the number of agents, how it grows, and yeah, yeah, here the case of two agents, maybe I'll draw it. This is just two agents driving towards each other, and they have to avoid the collision. If we have priorities, and the priorities are the same as the vehicle number, then vehicle 1 would continue on its reference trajectory, and 2 would avoid the collision, right? And if we look at the deviation of 2 from the reference, it is 2 times higher than if 1 and 2 divide a little bit from the reference. Right? So we continue to the next example.
Sorry, Bassam. May I ask a question?
Yes, please.
Regarding the previous graph, is there an explanation why suboptimality, let's say, of this method has to do with the number of agents, or it is random?
It depends on the application in this example. The suboptimality of time depends on the number of levels, and the suboptimality of the solution, I would say it depends on the application in the first hand.
So the number of agents, we cannot tell something, a correlation from that it affects in somehow. If for example the solution is improving or not with a number of agents. This is just a graph that we cannot learn a lot. I mean, considering the number of agents. I mean,
no. Here I'll show you a simulation video in a minute, and you will see why it is like this.
Okay, thank you.
And here we see another example of vehicles driving in parallel. And here are the reference trajectories. There is an obstacle on the way of the vehicles. I'll show you in the simulation video where the obstacle is located, and they have to avoid the obstacle. And avoiding the obstacle, they have to avoid each other also at the same time. And here again we see the computation time if we take CMPC, and here we see the computation times of parallel or priority-based non-cooperative DMPC and sequential non-cooperative DMPC. And here you see that again here it is larger or equal 1. So we take the objective value of the priority base and divide by the objective value of CMPC. If we have just one vehicle in our network, and this is this example here, then CMPC and DMPC deliver the same result, right? We have just one agent. So if it is CMPC or DMPC, we have the same result. That's why here the objective values are equal. So this change of the objective values between worse than CMPC and equals to CMPC, I'll show you also in the simulation video why this happens and why it decreases with time, with number of agents. So we will see this in a minute. So, but first I have to go through this slide with you. So application to vehicle decision making. The application to vehicle decision making combines high-level control methodologies and requirements of autonomous vehicles within a networked framework, right? So Net-MPC combines both. So networked vehicles are dynamically decoupled agents. We discussed this. Couplings are functions of subset of the states of a vehicle and a subset of the states of its neighbors. As I explained you, it depends on what we couple. So active agents are vehicles and passive agents are obstacles in this network. Net-MPC unifies collision detection. We don't need an algorithm for detection. This is automatically done in the prediction horizon. Avoidance trajectory planning, because MPC in general can at the same time detect the collisions in the prediction and plan an avoidance trajectory. Yeah, and trajectory following in one optimization problem, because the trajectory we plan is planned using the control input. So we don't need to have a second controller to follow the planned trajectory. So the method I presented is efficient to find a solution to the optimization problem of vehicle decision making, and in general, decision making algorithms are non-convex optimization problems. And here pay attention to the A solution, because we don't argue that we find the solution. So that optimal solution, we find just a solution. So now is time for looking at videos. We will first look at the example of vehicles driving in parallel. And here maybe it is good news for Shao and Julia. We are using here mixed integer quadratic programming. Yeah, the control strategy is first, I'll firstly show you the results of CMPC and then the results of DMPC. And if I say DMPC, I mean here always the priority-based, non-cooperative, distributed model predictive control, right? So we look again at this example. I try to explain everything here. So the scenario is two parallel. The number here is related to the number of agents, right? Optimizer is mixed integer quadratic programming. The strategy we use here is centralized MPC. And here you see the stamp number we are now in, and here the time. And on the left-hand side, you see the control inputs of both vehicles. So you see here now, they are 0, also in the prediction horizon, because the reference trajectories of both vehicles are the straight lines, and they are already on the straight lines. So in the way of the red vehicle, it should be here vehicle number 1, is an obstacle. It's located, its center is located on 0, 0 in the origin of the coordinate system. So we continue. So the vehicles till now didn't detect the obstacle. The obstacle is until now not inside the prediction horizons of the vehicles. And now something happens. The vehicles detect the obstacle. The centralized MPC find an optimal solution to guide one vehicle to the right and the other vehicle to the left of the obstacle. So you may think also using your brain power that this is the optimal solution, right? So guiding the red vehicle to the left or guiding the yellow vehicle to the right together with the red, of course, is not the optimal solution. So I need to get water. Okay, understood? Fine. So the vehicles coordinate using centralized MPC to follow their reference trajectories and avoid the obstacle. When avoiding the obstacle, they have to avoid each other. And after the obstacle, they have to go back to their reference trajectories without colliding with each other, and this works. Now we look at the same example, but using DMPC. And here, randomly, we can get the same solution as CMPC. But I forced the vehicles here to get a worse solution than CMPC by moving the obstacle slightly to the south to make it better for for the red vehicle to drive to the left from its point of view, right? Just to show you that there is a difference between CMPC and DMPC, right? So the red vehicle has the higher priority 1, and the yellow vehicle has priority 2. And the red vehicle, or for the red vehicle, it is better to drive to the left because, as I said, I shifted the obstacle slightly to the south to make it better for the red vehicle to drive to the left. And the yellow vehicle has to react to the red vehicle and to avoid the red vehicle, and they coordinate and get back to the reference trajectory. So you see that we get a solution. It is not the optimal solution, and I forced the MPC to not get the optimal solution to show you that accidentally you can get the optimal solution, but this is just accidentally. Randomly could happen, but you cannot guarantee this. So now we...
Sorry, so in that scenario, the priority assignment is kind of like situation dependent, right?
Yes.
Because in case if you assign the priority to the upper vehicle, then the problem gets infeasible.
No, in case of 2 vehicles, it doesn't get infeasible. Of course, infeasibility in this sense depends on the prediction horizon and on the limits of the steering angle. I forgot to mention that here the vehicles are driving with the same velocity. That means we cannot change the velocity here to avoid collisions between the vehicles, right?
Yeah, so how exactly do we assign the priority? Like since like the obstacle is like kind of unknown.
Yeah, if it is unknown, of course, this is an example where I would like to show you that the priority assignments also depends on the application. In this application, if I was speaking about 2 vehicles, now we have 6 vehicles, and we are using centralized MPC, so it will work, right? But in case of DMPC, if the priorities, if we assign, for example, here, the yellow and the turquoise vehicles, this is cyan, I think, this color. The yellow and cyan vehicles higher priorities than the red vehicle, then it will not work, right? So they will not, maybe I can draw it here. So if I have vehicles driving in parallel, and the priorities are 1, 2, 3, and assume that there is an obstacle in the way of 3, which is not detected by 1 and 2. That means 1 and 2 will continue on the reference, and 3 should avoid the obstacle, right? It's not possible because 1 and 2 will not move for 3. So the priority assignment here is essential to get a feasible solution. So as I told you some slides before, I show you an example where the priority assignment can lead to infeasible solutions. So the right priority assignment here is 1, 2, 3, always from the middle to the outside of the formation. So we continue watching here. It is CMPC, and we have 6 vehicles. So the best solution is to guide 3 vehicles to the right, 3 vehicles to the left, and they would coordinate using CMPC, of course, to avoid the obstacle, avoid each other, and get back to the reference trajectory. And now we look at the same example using DMPC, and the obstacle in front of the red vehicle, I have moved slightly to the south to make it better for the red vehicle to move to the north to show you the difference between CMPC and DMPC. And the priorities assignment is here, from inside the formation to the outside. So I hope you're seeing my mouse cursor. So we have here 1, I think 2, 3, 4, 5, 6. Right? This is the logic in distributing the priorities here. Yeah, and they coordinate and get back to their reference trajectories. Now we look at the example of with the circle using 2 vehicles. You see here 2 vehicles driving towards each other, and they have to follow their reference trajectories and avoid each other. And yeah, it works. So each vehicle deviates a little bit from the reference trajectory, and yeah, they get back to the reference trajectory after the collision area. And now we look at priority-based non-cooperative DMPC, and I showed you this in pictures. So the red vehicle follows its reference trajectory without counting for the yellow vehicle, and the yellow vehicle avoids the red one and gets back to the reference trajectory. And now we look at the same example using 6 vehicles. And here it is the example, what I showed you, that we have a circle. On the circle, we have distributed vehicles, and we have here in this example 6 vehicles. It's an even number, means that the vehicles would change positions driving through the center of the circle. And you see now they are moving naturally, right? It is using the centralized MPC. It's more like yeah, a roundabout. Yeah.
Question. Thank you. This video, if you go back a bit to see the trajectories, why do they all turn to the right, for example? Because I think that they are symmetrically placed, right?
I didn't get the point.
So I mean, like all of them are symmetrically placed.
Yeah.
And why does the solution of like, why isn't it the case that they also try to avoid each other moving to the other direction? Is there kind of a rule, or is this just a solution given by the problem?
So the task is, go back. So that in the scenario, we distributed vehicles on a circle and told the vehicles to drive on the diagonal to the other side, right? And in this scenario, if the number of the vehicles is even, then you switch also implicitly the positions of the vehicles, right?
Yes.
Yeah.
My question is, for example, for the red vehicle, in the prediction horizon, it can see the green and the blue one, right? And because of symmetry, it can both choose either to go left or right, because there isn't.
Okay. Your question is why they are moving to the right?
They follow the same rule of deviating all of them to the right, but who says to do so? I mean, why isn't some of them? Do you understand, right?
Yes.
Okay.
I understand you totally. This is a different question. This is a question of non-convexity. And actually, the DMPC decides on this solution. So there is no coordinator, nobody saying go to the right or go to the left. But if they in this example all have to go to the same direction to find a solution. If one of them decides to go to the other direction, we will not find a solution.
So there is not an additional rule. This comes naturally as the solution to the problem.
Yeah.
Okay, thank you.
Yeah. It is randomly. It could happen also that they coordinate by moving to the left.
To left. Okay, thank you.
Yeah. So randomly we are in a right driving country, so it happened. Yeah. So we watch it again. And why I am choosing this example to show you that distributed MPC is not always a good choice, right? Because, for example, here we force the vehicles to drive with constant velocity. That means it's just only possible to avoid each other by changing the direction, means the steering angle. And in case of priorities, you will see now, so the red vehicle is assigned the highest priority. That means it will continue on the straight and it will not change its direction. As I remember, we distributed the priorities here, maybe Patrick, you can correct me if you know it better, counterclockwise, right? Okay, that means the yellow vehicle considers the red, the cyan considers the yellow and the red, the blue considers the cyan, yellow and red, the, I don't know, maybe orange, this color, considers the blue, cyan, yellow and red, and the green considers all other vehicles, right? And if you look at the solution, it's not natural, right? It's not like a roundabout. And I want to show you in this example that distributed MPC, or the method here of priority based, is not always a good choice. It depends on the application. So you see, we avoid the collisions here, but this is not applicable to road vehicles. Maybe in the case of Maximilian is no problem. You have the air, so you can move in the air as you would like. Right. So that's all about this video, and now I'll show you an experimental video. So maybe a question could be asked in this case: what can we do if we don't get a solution, because we cannot guarantee finding a solution, right? So because we are dealing here with real-time systems, we cannot repeat the computations again and again and again. So we have to have always a solution, a backfold solution, and yeah, the general solution in such systems to go to an invariant set. And in an invariant set, in case of road vehicles, is just to stop. So stopping, not moving, avoids the collisions always. So if we don't find a solution, the fallback solution is always to stop. And maybe Maximilian, you can explain what happens with aerial vehicles.
Well, for multi-copters, it's okay to stop, but imagine the airplane stopping. I don't know if this is a good fallback solution.
Yeah, so the invariant set in the air is a circle, and maybe you know the term loiter circle. Yeah, maybe you have experienced it, maybe by traveling by plane, that during Corona, hopefully. Maybe after Corona, you can notice this. Sometimes the plane arrives to the airport, but it doesn't get permission to land. And what the plane can do, the plane goes for a loiter circle. Yeah. Well, let us look at here an experimental result. Here we see two vehicles driving towards the obstacle here in the middle. So it is the same example of two parallel, but now with experimental vehicles. It's more exciting. And you see here the solution of centralized MPC. The vehicles avoid the obstacle and each other and drive back to their reference trajectories. And now we look at the solution of DMPC. So I here again forced this vehicle, the inner one, to avoid the obstacle to the left by moving the obstacle slightly to the right to make it better for this vehicle to avoid to the left. By the way, this vehicle has the higher priority. So the inner one has priority 1, the outer one has priority 2. So one has to avoid the obstacle, and 2 has to avoid the obstacle and number 1. And here we see that 1 avoids the obstacle and 2 reacts to it, and they coordinate and get back to the reference trajectories. And now we look at the circle example using 2 vehicles. Using centralized MPC, they avoid each other and get back to the reference trajectory. And using priorities, we will see it in a minute. One of the vehicles will continue on the reference trajectory and the other vehicle will take care of the collision avoidance. So it is the left vehicle. So it avoided the collision and got back to the reference trajectory. So, and we look at a different example of pose control. This is what no, this is not pose control. Oh, it's pose control, okay. So I explained it to you. It is the example of go-to formation. We have N vehicles, N agents at arbitrary starting positions, and they have to drive to predefined goal positions. They have to minimize the traveling time and coordinate to not to collide with each other. And here we see the centralized solution. So they drive to their targets. So that so the goal is this formation. And now using DMPC, so they coordinate. You see that it is suboptimal in comparison to CMPC. And they find a solution. Now let us look at the intersection example. And maybe you can look at directly at the example with more vehicles. So this is what Manuel proposed to distribute the priorities in a certain distance of the vehicles. So here we have an area where we distribute priorities, an area where the vehicles wait for planning, an area where the vehicles plan, and other here are vehicles who passed the intersection or are not yet in the planning area, in the other areas. And you see here the task of the vehicles to cross the intersection as fast as possible. They have to coordinate to not to collide with each other, and it works using our DMPC. And we look now at the last example of today, and it's an exciting example. I like this example because here we have 2 goals. Maybe I also go directly to the higher number of agents. Right. Here we have a number of agents. They have to drive as fast as possible around the racetrack here. And why I like this example, because the vehicles here have to avoid each other, but at the same time, they compete to be as fast as possible. So they have at the same time to block, as you may know from Formula One racings. So they have to block the ways of each other and at the same time to avoid each other. So the rules of Formula One, it's allowed to block, but it's not allowed to collide with other vehicles. So they managed to do it, and yeah, it's really exciting example of network agents. So one of my former students applied our DMPC and optimization methods also to aerial vehicles for airborne wind energy with multiple wing system. Maybe you have seen it. If not, no problem. I just want to show you that it's applicable in other areas also. So a summary of the MPC, it's developed for NCS consisting of dynamically decoupled agents. The coupling happens in the objective function or in the constraints, and we consider time variant coupling. We satisfy the prediction consistency property, and we get NCS stable and feasible solution. And using the levels of computations, we can reduce the computation time. That's all about the network. So thank you for also your questions during this lecture. I planned 1.5 hours for the lecture, but we took more than 3 hours. But I'm happy of that because of the interaction also between us. It worked very well. And I hope you understood the main ideas I presented. It's not necessary here to understand each single word, just to understand the concepts and yeah, to transfer them to the lab exercises. So do you have questions on the network stuff? Maybe discussions, maybe remarks.
Just a very short one. So the giving of the priorities, the prioritization part, it was quite randomly here. So it was depending on the scenario, and at the beginning you decided who has which priority, right?
Yes. Yes.
Okay, so there's no algorithm to adaptively distribute the priority in case of any distances or anything like this.
Yeah, this is the research topic of Patrick now.
Okay, sounds interesting, Patrick.
So he is looking at priority distribution to reduce the computation time and to enhance the feasibility and quality of results. And what you have said, it's a smart idea to have an adaptive priority distribution, and this is indeed the current topic of Patrick.
I just have a related question. Like in case of, for example, unknown obstacles, I mean, is that even possible to predetermine priorities because you don't have any information about like the future obstacles?
No. So no information, no decision making.
Yeah, so I feel like this priority-based MPC approach works kind of like in like a structured environment, right? Not in a environment with unknown like future informations. Is that correct?
this is in general for control, correct? So if you don't have information, it doesn't matter if you use centralized or distributed MPC in general. It doesn't depend on the method you apply. If you have missed information and you don't know, you don't have information about, for example, what you said, an obstacle. How do you want to count for this obstacle? I mean, we distinguish here between completely missed information and between maybe data losses. But you're right, in general, for priority distribution, you need a structured environment. And of course, this is not related to the information. Always you need the information, but priorities introduce a structure in the system, right?
Yeah, yes.
Yeah. And of course, as you learned in your study, probably there are always different solutions, and it depends on the application which solution you would choose to solve the problem you are facing. So there is no general solution for everything. So do you have further questions, or are you hungry like me? So actually I am hungry and I prefer to continue after the break, but we will continue with the lab. But of course, if you have questions related to anything, of course, we are ready to discuss with you. So Patrick and me, will be back at 2 o'clock. And for you, the room is open. The breakout sessions will be started now by Patrick. So you can start before us with your teammate working on the lab exercises. So have a nice break.